students, welcome to TS Booklearn. This is a new chapter, that is real numbers in class 10, exercise 1.1. So use Euclid's algorithm to find the HCF of 900 and 270. Using HCF algorithm we need to find that. How to find that is 900 can be expressed as 270 into 3 plus 90, and 270 can be written as 90 into 3 plus 0. At this point of time we have 0 as a remainder, so we need to do this process until we get the remainder 0. Its division algorithm is divisor is equals to quotient into dividend plus remainder. So we are following the same procedure. So HCF will be 90. Second bit, 196 and 38220. If we do 38220, here we are taking the highest number 38220. This can be expressed as 196 into how much number we get, so that we'll get the remainder 0. 196 into 195 plus 0. So 196 itself is the HCF, because here at this point of time we got the remainder 0. Third bit, 1651 and 2032. If we do 2032, if we express 1651 into 1, how much will be left out is 381. So with that 381 again we have to multiply it so that we get some remainder, plus 127 we get 1651. So if we check here, still the remainder is not 0 here. So 381, if we check 127 into 3 plus 0, HCF will be, because here we got the remainder 0, so 127 is the HCF. So second bit is use division algorithm to show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So they are asking to find that odd integer of the form 6q plus 1, 6q plus 3, 6q plus 5. So q is some integer. Let a be any positive odd integer and b is equals to 6. So a is equals to 6q plus r. Since by division algorithm what we can say, a is equals to pq plus r, 0 less than or equal to r less than b. So r is equals to, what are the possible chances of r? It will be either if b is equals to 6, then the remainder will be less than b only. Here by division algorithm we can say that 0 is less than or equal to r less than b. So remainder will be less than b only. That is, we have taken b as 6, so it will be less than 0, 1, 2, 3, 4 and 5. Those were the only possibilities. So therefore a can be, a is equals to 6q plus 0 or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5. We have just substituted in place of r as 0, 1, 2, 3, 4 and 5. Here r is a remainder and q is a quotient, right? So but a is taken as an odd number, therefore a can't be 6q plus or 6q plus 2 or 6q plus 4, because they told that it is an odd integer, odd number. If it is an odd number, we cannot say 6q is a odd. For example, if we see, if let us say q is equals to 1, 6 into 1 is 6, it is an even number. 6 into 2 is 6 2s are 12, that is even. 6 3s are 18, that is also even. 6 4s are 24. That is also even. Similarly, if we take 6 cube plus 2, then 6 ones are 6 plus 2, 7, 8. It is an even integer. If we similarly if we check for 6 cube plus 4, 6 ones are 6 plus 4, that is 10. That is also an even integer. So take as many numbers as you want, but you will not get the even odd number. So we cannot take 6 cube plus 2, 6 cube plus 4. So any odd integer is of the form 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. You can try it using trial and error method. If you want to try, you can try using 6 in place of q, substitute with the numbers and check whether you get odd number or even number. Coming to the next bit, that is use division algorithm to show that the square of any positive integer is of the form 3p plus 1. So let us do this. Let a be a positive even integer, then a is of the form 2p and a square is equals to 2p whole square. So take a be any positive even integer, then a is of the form 2p. So a square is equals to 2p whole square. 2p whole square will become 4p square. It can be written as 2 of 2p square. We can write it like this. 2 into 2 of p square also we can write. For example, if we take 2p square as k, it is also an even integer. So because if we multiply anything with k, we'll get even integer only. If a is an odd number, then a is of the form 2p plus 1. So if a is an odd number, then a is of the form 2p plus 1. A square is equals to 2p plus 1 whole square. If we expand it using a plus b whole square formula, 2p whole square plus 2ab plus 1 square. If we solve this, we'll get 2k plus 1. So k is equals to, in the above k, what is the k? We have 2p square here. If we check, so where p is a quotient, zero, 1, 2 are the possible reminders. A can be considered as square of an integer. So a can be considered as a square of an integer. Any square number is of the form 3p or 3p plus 1. So here we have proven that if any square number is of the form 3p or 3p plus 1. If we check here, we have let a be any positive integer that we have expressed as 2k. And here if we check in the down, if a is any odd integer, a is of the form then 2p plus 1. Then we have solved and given that 2k plus 1. Here p is a quotient and 0, 1, 2 are the possible reminders. So we can say that a can be any square of the integer is of the form 3p or 3p plus 1. 3p plus 1. Coming to the next bit, that is use division algorithm to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Let's think that let a be positive integer and consider b is equals to 9. So we'll think b is equals to 9, a is equals to b cube plus r. By division algorithm, we can say that a is equals to b cube plus r, then a 0 less than or equal to r less than b. What will be the possible reminders? 0 or 1 or 2 or 3 or 4 or 5, 6, 7 or 8. It should be less than 9. So a is equals to 9 cube plus r. Cubing on both sides. If we check, if they asked for cubing, right? So we are cubing on both sides. A cube is equals to 9 cube plus r whole cube. And we have a formula for this. A cube plus 3a square b plus 3ab square plus b cube. This is the formula for a plus b whole cube. So if we expand this using this, we'll get 9 common here. If we expand this and solve this, we'll get 9 common here. So we can write it as 9. If we think that whole after taking 9 common, if we check whatever left out is 9 square cube 3 into 9 into q square r plus 3q r. If we take that as m plus r3 r cube, we can say that a cube is equals to 9m plus r cube. About r, it will be less than 9. That means if r is equals to 0, r cube is equals to 0, then 9m plus 0, it will be 9m. If r is equals to 1, then 9m plus 1. If r is equals to 2, then it will be 9m plus 8 if we solve. If r is equals to 3, then a cube will be 9m plus 27. If we solve that further, we'll get 9m again. Similarly, if we check for r is equals to 5, it will be 9m plus 125, 9m plus 8. If r is equals to 6, you will get 9m. If r is equals to 7, you will get 9m again. If r is equals to 8, you will get 9m plus 8. So this can be solved like this. So a cube is either in the form of 9m or 9m plus 1 or 9m plus 8. By using the above, we can say that it is in the form of 9m plus or 9m plus 1 or 9m plus 8. Next bit is fifth one. Show that one and only one out of n plus 2 or n plus 4 is divisible by 3 where n is any positive integer. So case 1 is let n be any positive integer and consider b is equals to 3, because they said that it is divisible by 3. Then from Euclid's lemma, what we can say, n is equals to bq plus r. So b is equals to 3 we have taken, n is equals to 3q plus r. That is, if it is then what is, by division algorithm we can say that it should be, if a is equals to bq plus r, what is that, and 0 less than or equal to r less than 3. What is the possible chances for r is 0, 1, 2, 1 or 2. If r is equals to 0, then we can say that n is equals to 3q plus 0, n is equals to 3q. If n is equals to 3q will be divisible by 3, because 3 into something will be divisible by 3. And n plus 2 means 3q plus 2. 3q plus 2 means it will not be divisible by 3. You can check it, because if you take 3 into 1, we'll get 3. If you take 3 into 2, 3 2s are 6, 3 3s are 9, 3 4s are 12. So all will be divisible by 3. If you take 3q plus 2, it is not divisible by 3. If you take 3 1s are 3 plus 2, it is 5. It is not divisible by 3. Similarly, if we take n plus 4, 3q plus 4 means 3 1s are 3, plus 4 is 7. 7 is not divisible by 3. n is equals to 3q is divisible by 3. 3q plus n plus 2 is not divisible by 3, and n plus 4 is not divisible by 3. So n is equals to 3q plus 2 is not divisible by 3. n plus 4, if we check, 3q plus 2 plus 4. We check that 3q plus 6. Here if we check, we are first checking for r is equals to 1. For r is equals to 1, n is equals to 3 plus 1. For r is equals to 2, n is equals to 3q plus 1 plus 2. For r is equals to 2, we are checking all three conditions, n is equals to 3q, n plus 4 and n plus 2. So in all the above three cases, we observe that only one of either n or n plus 2 or n plus 4 is divisible by 3. To understand clearly, I will show you once again. So to understand clearly, In first case, we are taking n as r is equals to 0. There are three things. First, n plus 2, n plus 4, and we have taken remainder as 0, 1 or 2. So for n it will be 3q. For n plus 2 it will be 3q plus 2. For n plus 4 it will be 3q plus 4. Out of these three things, n is equals to 3q will be divisible by 3. Similarly, for case 2, we are taking r is equals to 1. Here we have just seen only for r is equals to 0. For r is equals to 1, we are checking again. N is equals to 3q plus 1 we are taking. So, which is not divisible by 3. N is equals to n plus 2 is equals to 3q plus 1 plus 2, because n is 3q plus 1 only and this 2 is n plus 2. If we see this, it is divisible by 3. The next thing is n plus 4. 3q plus 1 plus 4. 3q plus 5, which is not divisible by 3. Out of these three things, n plus 2 will be divisible by 3. Here in third case, if we check, now we are taking r is equals to 2. We have only three possible reminders, that is 0, 1, 2. So 0 completed, 1 completed, and now we are getting into 2. N is equals to 3q plus r. That means n is equals to 3q plus 2. It is not divisible by 3. N is in place of n, if we substitute 3q plus 2 plus 4, we get 3 of q plus 2. It will be divisible by 3. If we check n plus 2, if we check 1, n plus 2, 3q plus 2 plus 2, 3q plus 4, it is not divisible by 3. So in all the above three cases, we observe only one of either n or n plus 2 or n plus 4 is divisible by 3. That means here, if we check here in the second case, n plus 4 case, it is divisible by 3. Here in case 1, in case 1, in case 1, n is divisible by 3. In case 2, n plus 2 is divisible by 3. In case 3, n plus 3 is divisible by 3. So we have proved that out of only one out of n plus 2 or n plus 4 is divisible by 3, where n is any positive integer. Thank you.